Deep dive into scikit-learn's KNNImputer. The KNNImputer in scikit-learn sklearn is a powerful tool for handling missing values in your dataset. It works by utilizing the concept of k-nearest neighbors, a fundamental algorithm in machine learning, to impute the missing values. Here's a comprehensive explanation. 1. The problem of missing values. Missing values are a common problem in real-world datasets. They can arise due to various reasons like data corruption, data entry errors, or simply incomplete information. Directly using datasets with missing values can lead to problems in your analysis and model training. Model errors. Algorithms often struggle with missing values, leading to unexpected results or even crashing. Data skewness. Missing values can distort the distribution of your data, leading to biased insights. Reduced accuracy. Missing data can hinder the accuracy of your machine learning models. 2. KNNImputer. The solution. The KNNImputer tackles missing values by leveraging the principle of similarity. It finds the k-nearest neighbors to a data point with missing values, based on the available features, and uses the values of those neighbors to impute the missing value. 3. Key concepts. K-nearest neighbors. The algorithm identifies the k most similar data points to the one with missing values. Similarity is measured based on the existing features of each data point. Distance metric. The KNNImputer uses a distance metric, e.g., Euclidean distance, to calculate the similarity between data points. Imputation strategy. The imputer can use different strategies to determine the imputed value. Mean. It calculates the mean value of the nearest neighbor's corresponding features and uses it to fill the missing value. Median. Similar to the mean, it uses the median of the nearest neighbor's values. Weighted mean. A more advanced approach that gives more weight to closer neighbors. 4. YAML configuration explained. The KNNImputer in scikit-learn offers several parameters you can configure. YAML. Configuring KNNImputer in YAML format. Nimputer. N neighbors. 5 number of neighbors to consider. Weights. Uniform weighing strategy for neighbors. Uniform distance metric. Non-Euclidean distance metric for similarity calculation. Copy. True copy data before imputing. Optional. Defaults to true. Add indicator. False. Add a binary indicator for missing values. Missing values. np.none value indicating missing data. Explanation of key values. N neighbors int. This specifies the number of nearest neighbors to consider for imputation. A higher value means considering more neighbors. Weights. str controls how the neighboring values are weighted when calculating the imputed value. Uniform. All neighbors have equal weight. Distance. Closer neighbors have more weight, giving more influence to similar points. Metric. str determines the distance metric used to measure similarity between data points. Common options include: Non-Euclidean handles missing values in the distance calculation. Manhattan uses the Manhattan distance sum of absolute differences. Copy bool specifies whether to create a copy of the input data before imputation. Setting it to true is recommended to avoid modifying the original data. Add indicator bool adds a binary indicator feature to the dataset to mark which values were originally missing. This can be useful for downstream analysis. Missing values object specifies the value used to represent missing data in the dataset. Default is np.none. But you can use other values like -1 or none. 5. Usage example. Python. From sklearn, impute import KNNImputer. From sklearn, datasets import load iris. Load iris dataset. Iris load iris. X iris. Data. Y iris. Target. Introduce some missing values. x10, 0 np.none, x20, 2 np.none. Initialize KNNImputer. Imputer KNNImputer neighbors 5. Weights distance. Fit and transform the data. Zimputed imputer. Fit transform x. 6. Advantages of KNNImputer. Flexible, can be used for both numerical and categorical data. Handles nonlinear relationships, can capture complex relationships between features. Adaptive, adjusts to the underlying data distribution. 7. Limitations. Computational cost, can be computationally expensive for large datasets. Sensitive to outliers. Outliers can heavily influence the imputation process. Needs appropriate distance metric. Choosing the correct distance metric is crucial for effective imputation. 8. Important considerations. Choosing K a good starting point for n neighbors is 5. You can adjust it based on the dataset size and complexity. Handling categorical features. For categorical features, you might need to use specific strategies like k-nearest neighbor classification or one-hot encoding. Validation. Evaluate the performance of your model after imputation to ensure it hasn't been negatively affected. 9. Beyond KNNImputer. Simple imputer handles missing values using simple strategies like mean, median, or constant value. Iterative imputer imputes missing values iteratively using other models like linear regression or decision tree. Other techniques. Consider using more advanced techniques like multivariate imputation by chained equations (MICE) if you have complex data. By understanding the principles and configuration options of KNNImputer, you can effectively handle missing values in your dataset, leading to more accurate and reliable analysis and machine learning models. Remember to carefully consider the limitations and choose the most suitable imputation technique for your specific needs.